Welcome to After Hours Engineering, Episode 1, RISC-V Softcore. We begin our adventure by building a foundation built off of Makefiles, Verilator, TestBench, and modules. The Makefiles are basic and they focus on a specific task. For example, testing modules or testing the softcore processor. Because I chose to use System Verilog, that necessitates that I find and use a simulator that understands System Verilog, and that's Verilator. For test benches, we'll look at two different types, CPP assertions, similar to unit tests, and clock generators, which we'll use the majority of. We'll cover them both. As mentioned, our processor is designed around modules rather than a monolithic approach. This helps showcase the concepts and ideas of the RISC-V ISA without burying them in compressed, reduced, or complex structures. Our workflow consists of developing a module with linting enabled, coding a test bench, and then inspecting it with either a unit test or a graphing utility like GTK Wave. Before we confront the RISC-V ISA, let's take a look at a Makefile and a few modules, for example, a multiplexer, the register file, and an immediate. Here we have an example of a Makefile that's focused around the multiplexer, in this case the MUX4 multiplexer. We've listed it at the top. In the next section we have the files that are relative to Verilator. It is built out of CPP files and header files. Then we have our GTK Wave tool. Then we have our HDL modules. In this case, we just have one. That's the multiplexer. We have our output build directory. And then now we have our new simulation toolchain, which is Verilator in this case, instead of iVerilog. Now, Verilator has a ton of commands, but we'll only use about 3 or 4 of them. In this case, we're going to use the execute, the build, and the linting feature. Most of the time you'll use the compile or the go phony commands that I have here, these targets. So we'll be using Verilator. Now Verilator has several commands in it, but we'll only look at about 2 or 3 of them. In this case, the lint, the execute, and the build. Now if you call just the execute by itself or the build by itself, you won't get enough files to actually go ahead and run the GTK Wave viewer. You really need to run both of these in order to get an actual simulation to run. And that's what I do here. I called it compile, our target. So now, whenever we want to either lint, we would call our makefile with lint, or compile or execute. That's it. Most of the time, you'll probably either use go or compile and lint. Rarely will you call execute or build. And that's it. All of our Makefiles are going to look almost identical to this, except for this section right here where we will list more and more System Verilog files as we move along. Especially when we get to the softcore processor, you will have all the System Verilog files listed here, which there's about 10 or 15 of them. So there you have it. This is an example Makefile, and we're going to use this structure throughout the rest of the series. Here we have our MUX file, in this case a MUX4. I've chosen to break our MUXes down into individual modules, MUX2, MUX4, MUX8, so that it's better to see what's going on without mixing it into complex macros and functions. So in this case, I've converted our A09 into System Verilog, and in this case, all it did was switch the wires over to logic statements. But other than that, this is exactly a ternary-based multiplexer just as it was in the A09. The same thing can be said for the registers. All that we did was change wires to logic, and anything else like the always statement. This is specific to System Verilog. This is the synchronous version. The combinatorial is the asynchronous version of the behavioral blocks. So that's all I've done. This code is identical to the A09. We still have a bunch of inputs and one output, and we operate on the negative going edge of the clock, just like we did in the A09. The register file is an extension of that. Again, we have some parameters that define its size and shape, some logic inputs, and a couple of outputs, the two outputs. Our register file has two outputs, A and B. And just as before, we have a bank of registers that are 32 bits wide, and there are 32 bits and 32 of them. And I've added in a bit of some initialization code this time just to cut down on some of the examples so that we're not constantly loading registers. We can focus more on some of the commands other than loads and stores in this case. So I pre-populate the registers with values. The rest of the code is identical. We have negative edge triggered registers and asynchronously assigning outputs, just like in the A09. The immediate is new to ours. This is a RISC-V specific concept here where we have broken down the instruction into its pieces. I haven't talked about RISC-V yet, so I'm not going to cover a lot of these things, but all of these macros or defines right here are specific RISC-V ISA codes. The point of this is that we're actually a module that instantiates another module, in this case the MUX8, because RISC-V has several different instruction types, and each instruction type has some sort of immediate information that you can pull out of the instruction. Not all of them, but of a vast majority of them do. The I, S, B, U, and J for sure. Plus, we threw in the shifting amount for the logical shifting and the arithmetic shifting. So this is our first true actual RISC-V module. And again, we're now in this case we're using the always combinatorial. That's this block of code right here, and it drives right into the multiplexer as it is. So there you go. This is our first true RISC-V module. Okay, I couldn't resist. We're going to take a sneak peek at a Verilator test bench. This is C++ code to drive the multiplexer, the 4-input multiplexer. All of the Verilator test benches are going to look very, very, very similar to this. In this case, you're going to include the Verilator header files. We will include some specific generated header files that are generated after the fact. And then we have some specific functions that we've built up inside of a secondary file called miscellaneous.cpp. All Verilator files start, of course, in a main. They have an entry point. And you're going to initialize Verilator using the command arguments. Once you've initialized it, you can start constructing things. In this case, our header file, our module.h file, has an example that I got off of zipCPU that will conveniently wrap up our Verilator module into a class so that we can start calling methods on it. And we have a setup method, a show method, we have a timekeeping value here. This is the simulator step time. Then we can go to our module and ask for the core out of it, which is the Verilator version of the MUX4. And then some other internal things that we'll talk about. Again, this is a high-level view, so I don't want to go into the depths of a lot of these things right here. We call evaluate. In this case, I put 4 values onto the input of the multiplexer, and then I run enough clock cycles so that we can see the select input change every 10 clock cycles. It starts at 0, goes to 1, then 2, and then 3. This will select each one of the inputs. The intent with this test bench is to verify that the multiplexer is working. Now with each one of these loops here that it goes through, the time step is incrementing one by one, and eventually it'll hit 10. So at the 10th time step, we'll change to 0. At 20, we'll go to 1. At 30, 2, and 40, 3. This is a super quick overview of Verilator. We're going to go into Verilator much deeper in the next episode, but I just couldn't resist showing you a generic, general, super simple test bench written in C++ for Verilator. There you have it. We've reviewed a basic Makefile, a few modules based on the System Verilog HDL language, and we've seen a brief picture of Verilator. Since the last update, I've finished all the rest of the instructions, the I, the B, the J, the S, the R, and the U, and I've stubbed out a couple of the system calls, eBreak and eCall. In the next episode, we'll begin looking at the RISC-V ISA as it pertains to the Ranger RISC processor. So until next time, peace!